Okay, good afternoon, everybody. Can you hear me? Okay, great. So, good afternoon, everybody. We will, get started. So today, we'll talk about some tips in structural steel framing and connection design, like do's and don'ts. What are the recommended things to do, and what also recommended to be avoided when we are designing and detailing steel structures. Okay, my name is Mustafa Mohamed, and I am a professor at the University of Illinois at Chicago, and also a structural engineering consultant for various structural engineering firms in the U.S. and abroad. And one of my specialties is in practice and in research is steel structures. Okay, so in design, typically, we have more than one option, for designing, anything. Each one of us, would approach a design problem probably differently. And especially for the connection design. So we'll think of different types of connections. And of course, the detailing of each connection, may require certain things, that are different from other connections. So do we need stiffeners? We don't need stiffeners. Is it a bolted connection? Is it a welded connection? So we have many options, to do that. So the important thing here is not only the design, but also the fabrication of it. So understanding how this is going to be fabricated, what's easiest for the fabricator to do, and erect in the field is extremely important. So it's very important to give the fabricator flexibility to the options that we have for the connection design. So typically, in the US, in most of the US, we delegate the connection design, for example, and it's important to have that flexibility given to the fabricator. And also the same thing for the selection of the member types, that we're using, knowing what is available in the market and what's not available. So if there is a fabricator on the job from the beginning, it's wise to consult with the fabricator on what to use. For example, if we have a job that has HSS members, hollow structural sections, typically those are more expensive, let's say. So whether the use, would help the job or not, or can we have other options instead of those. So this is one important thing. So the best solution among all these depends on the local construction practices and the contractor preferences. So the local practices, meaning depends where you are. If you are in the south versus in the north, if you are in the east versus in the west, on what are the practices. So the US is one country, but the practices are different from one place to another, or from one region to another. Let's say like the Midwest is not like the South, it's not like the West, where there's seismic. So it's important to understand these things and discuss those early on the job. Okay, so in every design, it's extremely important to understand the constructability. If we can build this or not, is it easy to build it or not? Is there an easier way to build it than this way, for example, or not? Because constructability means economy. So if it's a really simple connection without any stiffness, this could be really affordable, let's say. But if we design for the same connection, a complex connection where there's a lot of stiffness and we're not sure about this limit state or that limit state, add a stiffener here, add a stiffener there, that will make it expensive. Although we're adding a small stiffeners here and there, but that will add to the cost significantly because that's material and also that is also weld, and that's also labor and time. Okay, so hours for the labor and also, hours on the job itself. Need a day to, maybe to install all these reinforcements, around the beams that are needed for certain load. So constructability is economy. So when you are designing a connection or in general even members, about what's the direction of the framing, and we'll talk about these things, today, but think about how they're gonna build it. So initially, of course, with people early on in their career, this may not be clear, so it's wise to ask. So I started my career as a structural engineer, working in a design office, and I learned many, of these things from the senior engineers in the office. They don't teach these things. I teach steel design. I don't focus on these things, in the curriculum typically, because I have material to cover, and this is true for all the professors. But based on my experience and my knowledge of this and the importance of this, I usually at the end of the course, I give a presentation that talks about, practicality, what's good to do and what's not good to do, okay? So principles of constructability, simplicity. Simplicity equals economy. The more simple the design is, the more economical your structure is eventually. Least weight does not equal least cost, always. Okay, so typically steel is charged by the tonnage. Okay, whether we have, let's say, 200 tons of steel or 250 tons of steel, yeah, we have to pay, let's say, for example, if it's 250, we have to pay for 250. If it's 200, we have to pay 200, but this is not the only criterion for an economical structure. I mean, the price of steel is one thing, but it's not everything. We always worry about that, yes, and we have to, but connection design is another important factor. Connections are expensive. So maybe, as you will see today, that we have to maybe increase the size of one beam, okay, is better and would be cheaper than having a smaller size that it will work for bending shear, but it will require stiffness and reinforcements. Okay, so stiffness, as I said, it's more material, it's more weld, for example, bolts maybe, it's more labor, okay, and time for the workers. So if you add all these, that's gonna be probably more expensive than increasing the size of a beam. Fewer pieces, greater economy. This is on the same point also. The less the pieces of steel on the job, the greater the economy of the structure is, okay? Efficient connection design, that's a reduced cost. So if we think thoroughly through the connection design, through the types of connections, that, we need, that will give us a reduced cost eventually. So give that initially some time, some thought, okay, to what is best to have an efficient connection design, which eventually will result in a reduced cost. Okay, reactions, beam reactions. So beam reactions, is an important thing, and I witnessed that in my career, in the different places that I worked on initially when I started my career. Connection design, where, and I recall I worked for two good firms. One of them, mainly in the US, all over the US, and they do nice projects. The other one is in the US and international, and I have seen that. So, okay, design the connection for 60% of the capacity of the beam. Design the connections for 40% of the capacity of the beam in shear. Design the connections for 50% of the capacity of the beams. I saw that in the offices, and I was instructed, to do that also sometimes. Now, that's not an efficient connection design, because typically these beams are controlled by flexion. Okay, they're controlled by moment, by designing for the moment, by designing for deflection. Okay, so shear typically will be okay, on those beams, unless of course we have really special case where we have a high concentrated load that we have to worry about. So instead of designing for 50% of the capacity. So here we have for example, W14 by 22. We can get the capacity for, for that beam from, tables in part 3 of the AISC manual, and see what is the capacity, for that beam, for, in terms of reactions. And, we'll find that this is more than 100 kips. Okay, so why do I need to design for 100 kips or more if the reaction is only 20 kips? So show the reactions on the drawings so the fabricator can design for these forces. Okay, and it's not gonna be, the fabricator is not gonna be designing it for 20 kips exactly, or for 100% utilization, or even 90% utilization. If you use a connection with 2 bolts, probably it's gonna be double this capacity. Okay, so this is an important thing. Show the reaction on the drawings. Excessive conservatism in connection design does not enhance safety. Okay, so because we may have, cases where if we have such, a note like this, we may have a concentrated load that we don't pay attention to. And I show you an example, and that will lead to unsafe design. So do not design connections for full shear strength of the member. Yeah, we just talked about that. Do not have notes on the drawing such as connections shall be designed to support the full shear strength of the member. So full shear, that's 100%. So I told you I've seen 40, I've seen 50, and I've seen 60% in design offices. So, and there's also a note like this that tells you 100%, which is the full shear strength of the member. That's very excessive, okay? And in a building that will drive the cost significantly. Imagine how many more bolts needed as a result. Imagine how many more welds and labor, needed, as a result. Do not show notes such as connections shall be designed to support reactions occurring from uniform load equal to 150% of the uniform load capacity of the beams from table 3.6 in the AISC construction manual. So these notes used to be, maybe still, I don't know, on the drawings by structural engineers. Okay, so design the connections instead of showing the reactions and giving more thought into the connection design. Okay, I'll just throw this note and I'm done with it. Let the fabricator deal with it. And of course, the owner will pay for it. Okay, so here 150%. So table 36 gives you the uniform load capacity of the beams. Okay, so some notes used to be 150% of the reactions of 150% of the uniform capacity. So that's excessively conservative and also could result in an inefficient design. So here, for example, we have a beam like this. So we threw this note on the drawings that should deal with it. Okay, but we have a beam that is supporting, let's say, a column or an equipment that has a concentrated load on it that's equal to 200 kips. That's at 2 feet from one of the supports, plus the uniformly distributed load that's on the beam. We will have reactions that are shown here. So on one side, we're close to the concentrated load, we have 234 kips. On the other side, we have 54 kips. So that node will not cover the 234 kip reaction. So you will end up with a connection that's not adequate for the forces and may lead to failure. Okay, so that's one example. So now with the computer programs that we have, you can generate reactions on on all the beams, and you can export DXF files, for the drafters and the designers, to arrange in drawings. So that's not easy to get today. So from whatever loads you have in your model, just export all the reactions on the drawings, on the framing plan, and let them deal with it. Or for selected, or you could add that manually. Okay, you can mark those up with some maybe contingency that you add to whatever reactions. So there's a way to control that. Moments and axial forces provide moments and axial forces. So if we have not only shear forces on the reactions or in the members, if we have moments and axial forces, add those, because they also will need to be designed for. The connections need to be designed for moments and for axial forces, and of course for the combination. So if we have a combination of moment, of axial, and for shear, we have to include that. So the moments of connection design, for moment connection design, and for example, moment frames or in cantilevers. Axial forces, axial loads are in braced frames, in truss members, in hangers, in drag struts. All these need to be designed for, let's say, truss. So for a truss member, for a braced frame, show the force on the diagonal in the braced frame. I mean, we did that all the time, with plus minus, for example, if it's wind load or something like that. So it would be compression, would be tension. Okay, plus minus 30 kips. This is the axial force in that member. So in that case, the connection designer needs what he or she need to design for. Okay. Trusses, hangers. So tension forces typically on the hangers show the force. You designed for it. You use that to design the hanger. So show it for the connection design, and also drag struts in the diaphragm, in the floor fitting. Show the force that that needs to be designed for to transfer load from one element to another, and eventually to say braced frame or to the shear wall or to the moment frame, okay? Okay, load combinations and direction of the reactions. So depending on the load that's applied on the element, we will have a direction for the moment. So the moment could be in one direction. If it's a gravity load, okay, the direction of the moment is known. If it's, let's say, a wind load, or if it's a seismic load, the moment changes. Okay, the direction of the moment changes depending on the direction of the load. So for each case, show what you have. Does the moment change direction on this connection, or is it in one direction only, maybe because it's a cantilever and it's due to the load? So show that. Follow building code requirements for connection design. Gravity connections and non-seismic, that's according to AISC 360. Seismic connections, that's according to AISC 341. Do not mandate connection design requirements beyond what's required by the code. Okay, so follow the code. So if it's, for example, AISC 360, use what's required per chapter J of AISC 360. Okay, you don't do, if it's a moment connection and the building falls within the system that you are designing, falls within AISC 360, not a seismic system. Okay, so just use AISC 360. You don't have to choose the moment from AISC 341 for that design. Okay. Do not use bearing bolt strength where permitted by the building code. So this is also something that comes up all the time. Do I have to use bearing connections, or do I have to use slip critical connections? So use slip critical connections where is it required. I mean, there are cases where you need to use slip critical. Other than that, use bearing type connections because they are also cheaper than slip critical connections. Okay, so slip critical connections need surface preparation. They rely on a coefficient of friction. We have some values in the codes. You know, there are different values for different surfaces. What we have, this has to be checked, this has to be guaranteed. So if you don't have to use slip critical, then there are many considerations that you have to take. So do not use notes on the drawing such as all bolted connections shall be designated as slip critical connections. There's no need. That's a lot of preparation, you know, for all bolted connections. Do not use notes on drawings such as connections within 3 feet or 1 meter of column, connections directly supporting columns, bracing connections, connections to plate girders. Okay, so do not, you know, group the connections, you know, like this. So put notes like the ones that are shown here, and then, okay, those have to be done like this or like that. So treat each connection as a connection, you know, the way it is, depending on the forces that are on it, depending on the requirements that are needed, you know, for that connection. Use bolt bearing strength for all standard or short slotted holes. Hole are used. So loads are perpendicular typically to the slots. So, I mean, typically that's what's recommended. You know, standard holes or short slotted holes, I mean, something they are easy for fabrication for adjustments also during erection in the field. Do not use notes on the drawing such as stair connections, cantilever connections, angle connections, connections support 50 kips or equivalent in metric 222 kilonewton or more. Okay, do not use that. As I said, treat each connection the way it is. Bolt bearing connections are also used in seismic systems with R equal 3. R is the response modification factor. Okay, so if R is greater than 3, then in addition to AISC 360, we have to use AISC 341, seismic provisions of AISC. Up to R equal 3, we don't have to use AISC 341, the seismic provision. So even for seismic connections, we can use bolt bearing connections. So keep that in mind, because some people think that, okay, we have to use slip critical connections for seismic connections. No. Bolted and welded connections. So pre-tensioned bolts or weld shall be used for the following connections. Also, like pre-tension connections, they don't have to be used everywhere. Okay, I mean, use snug tight connections where possible. Column splices in a multi-story structures over 120 feet in height. That's where we need to use pre-tension bolts or welds. Connections of all beams and girders to columns and any other beams and girders that brace the column in structures over 120 feet in height. So for those also, we need pre-tension connections. Now, pre-tension doesn't mean it's critical. This is very important. Pre-tension bolts does not mean that the connection is slip critical, and then you have to check the capacity of the connection based on slip critical, based on the surface, the friction between the surfaces, etc. Excuse me. So there are pre-tension bolts, but the connection is transferring the load by bolt bearing, okay? In structures carrying cranes over 5-ton capacity, roof truss splices, truss connections to columns, knee braces, and crane supports. In those, use pre-tension bolts or weld, of course, because that will prevent any slip. If you have tight, you may have slip. Okay, so which may affect the behavior of the member, and we don't know, it may lead to unfavorable behavior of the member, or the function, unfavorable behavior of the function of the member. Connections in machinery support and other loads that produce impact or load reversals. So any connections for elements that are supporting machines, that are vibrating on a structure that's load reversals, or there's if structure is receiving any impact. This happens a lot in industrial facilities. So in those cases, we would use pre-tension bolts or welds. Not specify on drawings requirements like avoid one-sided connection if possible, and do not use for beams deeper than 18 inches. So why do I need to limit the fabricator of what connection type to use? If a one-sided connection, like a plate, shear tab, single plate, okay, all these names, also single angle connection. Engineers like to use double angle connection, fine. They have good capacity and there are, reasons for, using them. If, of course, they're accurate. connections are high, you know, and the bolts would be in double shear, so that will increase the capacity. So I have a reason for that. But if that's not required, why do I need to limit fabricator of using double angle connection? The fabricator can use single plate connection if it's enough for the reaction. The fabricator can use a single angle connection if it's enough. The fabricator can use a seat connection if it's enough and if it's easier for the reaction. Do not specify on the drawings. All bolts shall be 3/4 inch diameter. All holes shall be 13/16 inch. Okay, do not specify that. So if the fabricator is designing the connection, let them choose the bolt size. Okay, they have the forces that you provided them with as a structural engineer. Okay, if they want to use 1 inch diameter, that's fine. Probably they can use 4 bolts instead of 5 bolts or 6 bolts if they are using 1 inch, diameter bolts. So do not, limit them of what they need to use. Fabricators prefer short slotted holes to accommodate tolerances and to facilitate erection, as I mentioned before. If it allows to use short slotted holes with snug tight bolts for most types for shear connections. And this is probably the most common. So they can use slotted holes, they can use snug tight, and this should be appropriate for, maybe all the, floor framing, members. And these are most of the connections in a structure. Okay, let's say floor, how many beams do we have in that floor? How many cross beams do we have in that floor, like beams and girders? And how many connections, we have? A lot. So this type is preferred. It's easier for the fabricator, so can use it. According to AISC 303/16, which is the AISC Manual of Standard Practice. Okay, AISC Manual of Standard Practice. So the owners are designated representative for design shall indicate one of the following options for each connection. So this is related to the delegation of the connection design to the fabricator. How do we delegate the connection design? So the AISC Manual of Standard Practice, gives us what we need to use. So the options are: the complete connection design shall be shown on the structural design drawings. All the connection design should be shown on the structural drawings. And this is typically required in California. And actually some engineering firms, they prefer to do it that way. Okay. In the structural design drawings, second option, in the structural design drawings or specifications, the connection shall be designated to be selected or completed by an experienced steel detailer. So you give them the forces and let them select them and design them, and then you can review them as a structural engineer. In the structural design drawings or specifications, the connection shall be designated to be designed by a licensed professional engineer working for the fabricator. This is also good. So, and now all fabricators have professional engineers who can stamp calculations and drawings and do the connection design. So you could put that in your notes, in your general notes or in the specifications, and then you can review calculations and review the connection design, shop drawings as a structural engineer. Now, if 2 or 3 are selected, meaning delegated the connection design to the fabricator and are not having every connection on the drawing, The following shall be provided in the design drawing. So if you choose to do that, then you have to provide the following. Any restrictions, any type of connections. So if there is any restriction in a specific type of connection that you think is not appropriate for the functionality of your structure, say that. Indicate that, not because you don't like this type of connection, or you prefer this over that, or that's what's typically used in practice over that. So maybe this fabricator prefers something else. All data concerning the loads, shear moments, axial forces, transfer forces that are needed for the connection design. All the data that are needed for connection design, have it there. Remember, you are an engineer, you can design the connection design. You can do the connection design. So to do the connection design, what do you need? You know, if I'm designing a connection now, I know what I need, what type of forces I need, and the geometry I need, and how the the geometry should look like, and how the beams are coming together. You know, I designed the members, so I know how the connection should be. So, and the loads. So have that information there with the loads, and let the fabricator deal with it. So I'll give you an example, including even in California, projects. We did, for example, let's say braced frame connection. I'm talking about seismic braced frame, like special concentric braced frame. So we put the geometry. We showed the parameters of the geometry, A, B, C, D, etc. And we had a table showing what is A, what is B, what is C. So the fabricator can see all that. And of course, we have the forces as well. And for the completion of the design, we will also show, what is needed for that design. But for example, if it's not in California, you can have that braced frame geometry, okay, with a table showing all the dimensions that you need. And also all the forces that you need for different types of braced frame connections. So this way, the fabricator has the geometry and has the forces. Okay, and let them design. Welded, bolted, if they need, of course, any configuration different. If you put something, if they recommend something else, sit with them. And this happens all the time, by the way. You put a type of connection in the drawings, and then the fabricator calls you, hey, we looked at this. I mean, do you think if we use this, would work? Would be okay? Oh, take a look at it. If you think it's fine, and this is easier for the fabricator, let's do that, okay? Whether the data provided are service loads or factored loads. This is very important. So you have to indicate, are these loads factored or no? LRFD design or ASD design to be used. This has to be dictated by you as an engineer. Okay, the fabricator knows both, but how you design the building, what forces are these, and you indicate that in your notes. So connections need to be designed using the LRFD procedure or ASD procedure, etc. Okay, delegate connection design to fabricator, but do so properly. Just like we said before, provide all the information, delegate it, but do it properly. Specify code for non-seismic connections. For example, if it's R equal 3 or less, AISC 360. For seismic connections, specify the code to be used as AISC 341. So specify that. Framing to columns. Frame girders to column flanges. So the girders to the column flanges, the beams to the column web. Okay, the girders typically have larger loads, and also the flange width of the girder typically is larger than the beams because the girders are supporting multiple beams. Okay, so the flange width of the beam, probably it will fit between the column flange, okay, as you like you see in the figure, and then the girders will frame into the flanges. Size columns to eliminate need for stiffeners. So when we design the connections for the reactions, that force need to be transferred to the column. Whether the moments, the axial forces from the moments or the shear forces, they need to be transferred by the column, right? We have a load path. So the web of the column need to be checked for these forces. The flange of the column need to be checked for these forces. So the flanges and the web may not support these concentrated forces that are on them. So what do we need to do? Add stiffness. Add stiffeners. Okay, that's not recommended because this is more work, more material, more labor, etc. So in a case like this, we can just increase the size of the column so it has stronger flange, thicker flange, maybe wider also, and also thicker web that can tolerate these forces. And typically from all the steel that's in the building, okay, the least cost is for the columns, which are also the most important members. So imagine how many columns do you have in a column? And then at the same time, how many beams we need for that floor? We need a lot of beams, but maybe we need 15 columns or 20 columns for that from at each floor. So typically the cost for the columns is less. Okay, so use a larger size. Make opposing beams same depth. So here, as you can see, the detail, the figure explains itself. So we may have a beam that is deeper on one side of the column than the other side, as you can see. Okay. Now, in a case like this, we would need continuity plates. Okay, the continuity plates that go from one flange to another, as you can see here. Okay, if the two beams are not on the same depth, then we would need a skewed stiffener like this, which would need to be cut at certain angles and need to be fitted directly. So that's difficult for fabrication, for welding from the top, from the bottom. So instead of doing that, use the two beams as same size, same depth. Okay, maybe same depth, not necessarily the same size. Okay. Use deepest practical column. Deepest practical column. So here you can see the issue with the columns is typically how we fit the connections, how we connect the beams to the columns. Are they connected to the web or to the flange? Okay, and if they are connected to the web, for example, you see here between the difference between W8, W10, W12, and W14 for the same connection. So W8, typically, we don't have much size left in the web to frame a connection. It will be tight, even erect the connection there. So use, W, instead of, for example, using W8 by 40 column, you can use W10 by 30, for example, if it works, and I think it will. Okay, W10 by 30, so the weight is less even for the W10 than the W8 by 40, but you can have more space for the connection. Okay, and this is one of the advices that I took, as a young engineer, when I was designing this. I remember my boss told me at the time, do not use W8 beams. W10 is the minimum. And you can see now, why it's true, okay? Orient columns to minimize skewed connections. So here, if you have, for example, the common size is typically wide flanges, I shapes that we use. So we may have skewed beams, on the connection. So look at this here. So using this one in the right here, so we have 3 straight beams with this orientation with 1 skewed beam versus, okay, I want to orient this, okay, to fit that column here, to fit that beam here. So I will end up with 1 beam with a straight connection and 3 skewed beams with 3 skewed connections that are typically difficult to build. Okay, so skewed connections typically are difficult to build. Okay, here is another example in the case of a braced frame. So maybe considering the geometry and the architecture and things like that, no, I mean, those can be handled in different ways, by enclosures, column enclosures, by the architects, etc. So we don't have to do that. Okay, I mean, of course, now with challenging architecture and things like that, certain things may have to be done. But maybe I will not use an I-beam. Maybe I will use a circular shape. And I will talk about that. Circular shape will give me circular column. I can fit any connection in it and it will be considered like a straight connection. Okay, so here is another reason, for using skewed connections that are expensive, but we need to avoid that. So square connections typically will result in a nice organized square columns. So you will end up with organized connection like this, for example. If it's skewed, look at what you have. So look at the left figure, that's for a square connection. If it's skewed, look how we are connecting to the side of the flange. We are cutting that beam, okay? Welding here, and we will end up with 2 rows, with 2 vertical rows of boards and longer shear connection like this. If we are connecting to the web, this is even worse. Look how many boards we need, and the longer the plate, and of course, considering the forces and the moment and the connection here, the moment that will end up in the web column, the design is getting more and more difficult. Yeah, and of course the constructability as well. Do not frame do not frame more than 1 beam on any side of the column. So in drawings, right, we use the beam is aligned, okay, and today we use Revit, and it depends on the standard that's followed at your firm, but typically we use a line. So you can have 2 lines coming like this, side of the column. Now, in the drawings, this looks okay, and I've seen this a lot. But when you come to the detailing of it, look what we have. So these 2 lines are coming like this, but it's not a line. There's a width for that beam, for the flanges. So in that case, you have to cut the flanges to make both come together, and you will end up with something like this. So because you cut the flange here, you have to reinforce it with an angle or with a plate, or maybe angles on both sides. So that's more steel, that's more weld, that's more labor, that's more limit states to check to see if the beam works or not. Reconfigure framing for steeply skewed connection. Okay, check the framing. I mean, maybe change it. If you have skewed or steepy, members. So here you have, for example, instead of having, 2 steepy elements, coming in a configuration like this on the left, okay, steep skewed connection like this, okay? So maybe you can use something like that. So have a beam between these 2, between this sloped one and between this straight one, have another beam, okay? And then configure the framing and just move this a little bit okay, and let it have a square connection with this additional member between them. Okay, so that's add a header to connect to take the reaction from the other beam. Okay, so that's configure the framing, change the framing to accommodate that. Configure framing to minimize skewed connections. So if we have something like this, okay, so we know the column locations. Okay, sketch the members, and see what options will give you less skewed connections. Yes, we can see that here, for example, on the left, see the members. If we, here we have these columns. Okay, at the top, they have this girder with a square connection between them. This column at the bottom, it will have a square connection with the beam coming from the top. Then we'll have a skewed connection here. And then here, this column is in that shape. And we'll have another skewed connection here. And we'll have another skewed connection here. Now, the connections between the beams, look at that. All the connections between the inside beams and the girders are skewed. Okay, so very few square connections with the columns, and the rest is skewed, versus the same shape exactly if we use this configuration on the right. So we have square connections with the columns at the top and here at the bottom. And then we have, for these two interior beams with the top, we will have two square connections instead of skewed. And then here we'll have skewed, that's fine. The shape is skewed, so we may have skewed. We cannot probably avoid 100%, but minimize them. This one is also skewed. Here we change the orientation of the column. It gives me better connections here. Could be, one of them could be skewed. One of them could be square. The other one would be square or slightly skewed. But this one here would be skewed. Okay, so if I have to use an I shape, that's what I will end up. But think of a way to minimize the skewed connections. Favor using circular column sections over square rectangular connections. Okay, so if we use this, for example, on the left, if we use circular column, okay, you can see all the connections are square. A connection with a circular shape, it's always square. There is no skew. But if it's circular, if it's a square shape like this, okay, so we will end up with skewed connections, as you can see. So if it's possible to use circular shape, use it. Connections interference at the column. So here you can see on the right, as I said before, drawing beams as lines doesn't show you the full picture like this. I mean, it's okay. In the drawings, it could be shown like that, but you as an engineer sketch it with the full width of the beam and see how would that interfere with, with the column flange or with the beam flange, the girder flange. Okay, so it could be shown like this on the right, but if you draw it, you will see the problem. You will see the problem. Okay, so try to avoid this by maybe configuring the framing or maybe using column shape, or maybe offsetting the beam a little bit more to have a square connection and without the need to cut shapes and elements from it and then reinforce it. Okay, increase beam depth to avoid web reinforcement. So see here, for example, we may have to have different elevations, for the beams. This happens a lot, per architectural requirements. So in a case like this, since here we cut a lot from the W14, Okay, not much left. We have 2 bolts, and then we have to reinforce it. Instead of doing that, use W18. Use more bolts, and then maybe with the web thickness and the more web depth, you don't need any reinforcement. Okay. So that's what you will have. If you have to cut, part of the flange, then of course you have to reinforce it. If you have, elements coming at a really sharp angle, like we have here. Okay, columns must have sufficiently wide flanges to accommodate beam connections. Okay, so the flange of the column need to be wide enough to accommodate connections. Okay, so I would say minimum recommended flange width is 6 inches to allow installing bolts from each side of the web. Okay, pay attention to that all the time. So when you choose a column, W10, W8 avoided. If you have to do it, do it. But if the connection is to the flange, make sure you have a minimum width of 6 inches. Okay, size members to have sufficient strength at net section. So in design, we design the beams for shear and for bending. So we have not come to the connections yet. So it's okay for bending and for shear, but when we come to the connections, okay, there are holes in the beam that will give us a net section eventually, or in the brace, okay? Could be beam, could be brace. So that we have to check the member for that net section. For tension, if it's a brace, for example. So instead of changing the member size, or maybe I have to do some other type of reinforcement and complex connections and adding plates and stiffeners to compensate for that, size it originally from the beginning to account for the net section. So there's a rule of thumb here. The maximum recommended stress ratio at the gross section is equal to the required strength divided by the usable strength equals 0.75 maximum. If you use that, then mostly the net section will be okay. Okay. Communicate and coordinate. So discuss with the architect if his design is creating structural inefficiencies. Okay, so discuss with the architect. So, okay, his design, okay, will result in maybe more steel because of this, because of that. So that's at early stages, and it's a very important stage where you and the architect, formulate the concept for the structural framing, for the building. Failure to proactively communicate may put you in a corner. I mean, whether it's legally or from a reputation standpoint, that you may end up with an expensive building, your design will result in expensive building, etc. Ask your client in writing for information you need and give dates to submit. Okay, so these things are important because they will affect you. Deadlines, right? Deadlines, and also information. Do you have that information in writing? So try to have all that in writing. And this is true for connection design, for everything. Anticipate what other consultants will be doing in order to avoid coordination problems and interferences during construction. So pay attention. I mean, of course, this comes with experience also. What other consultants need? I mean, like MEP, mechanical, electrical, plumbing. What do they need? So how does your design affect them, or their design affect you, etc. So that's why having, working as a team is important. Okay, for this is a problem because of lack of coordination, let's say for the MEP. Okay, so mechanical engineer is running a duct at that location. Nothing left in your beam. And where the high shear force is, which is at the end of the beam. So what do you do now? This is due to lack of coordination. So coordinate, okay, coordinate. So you avoid something, you know, like this. Do not delegate design of reinforcing around beam web openings. So if you need to reinforce, so for example, something like this happened, the beam is not going to work mostly, you know, a deep beam like this with high shear force will not work with this opening. So what do you need to do? You need to reinforce around that opening. You have to put angles here, angles there, or stiffeners, angles here, and angles here. And you need to design the weld and the angles, and you have to see how the load transfer from one end to another around the opening. There's a design guide for that. And there's an AISC design guide for web or reinforcement around web opening. Now, do not delegate this. You have to do it as a structural engineer. Do not delegate this design to the fabricator, okay? And there are other types also that you have to do it yourself, even if you are delegating the connection design. Okay, the Code of Standard Practice of Steel Buildings and Bridges gives us this notes, which will help in minimizing uncertainty among bidders, okay? So permanent bracing, column stiffeners, column web, doubler plates, bearing stiffeners in beams and girders, web reinforcement, openings for other traits and other special details where required shall be shown in sufficient detail on the structural design drawings so that the quantity detailing fabric requirements for these items can be readily understood. Show everything on the bidding documents. If you need stiffeners, if you need plates, doubler plates, if you need continuity plates, if you need web reinforcement, if you don't show that, they will come back and they will say, well, you know, our bid was not based on these. This is a lot. This would need $50,000 more towards probably the end of the job where not much money left. So you are in the corner. Okay, so this is important. Do not delegate design of plate girder welds. Okay, plate girder is a beam, and it's your responsibility as a structural engineer to design it, not the fabricators. Design of the welds of the plate girder is part of the design process of the whole plate girder. Plate girder is composed of 3 plates, as you can see, in one configuration. So these welds are part of the design. So that's not delegated to the fabricator. Think about connections that will be detailed where connection design is delegated to the fabricator. So if you have double plate girders like this, okay, how are we gonna do the connections here? Okay, so we're closing, you know, here the part inside is gonna be like a box. How can we access that? So, I mean, there are ways to deal with that. Okay, we have done it. But you have to do it as a structural engineer, designing the plate girders, not the fabricator. Okay, configure HSS framing for to simplify connections. So, you know, HSS sections, I mean, are tricky in connection design. And also if you cut them, if you cope them like this, you know, they are not like white flanges. Okay, these are cold roll typically. Okay, not hot roll. So, so coping these is not typical. So maybe you need to configure the connection and the framing to simplify the connection, as you can see. So this is, it's no for this, number one, it's yes instead for number two. Here is the same thing. Yes, for a simple connection connecting the HSS column to the wide flange beam like this. No for a through plate that will, you will have a hole here, you will slide the plate and then you will bring it from the other side and weld around it. So you have to cut the HSS from both sides. Through plate is a is a way to connect, you know, members to HSS columns, but try to avoid it. I mean, there are simpler ways, you know, to do that. Okay, welding tips to enhance constructability. Strive for downhand or vertical welds. So when you design the welds, you show the welds, try to do it, you know, downhand and vertical. Avoid specifying all around welds unless they are needed. Okay, many engineers do that, all around welds. Okay, so we don't need that maybe from a strength standpoint, you know, we don't need that. So why do we specify it? If it's two lines, only one from each side is enough, then let's just do that. So are we supposed to, we have a question here. Are we supposed to specify coping dimensions? Yes. So if, I mean, you would know what's needed, you know, to fit a beam inside the web of the column, let's say, or a beam into a girder. So you know what is the flange width that is conflicting with the top flange of the beam. So you know what that is. So the width of the flange is, say, 3 inches. So that's in your way. So you cut it 3 inches plus, let's say, ½ inch. Okay, to allow, you know, fitting that properly. So the answer is yes. You, as much as detail you can get into, this means that you understand your structure, you know, how it's gonna be built and how it's gonna be erected, okay? So, okay. Okay, and then what's the typical tolerance or gap for that? So as I said, so plus, you know, plus I would say ½ inch, that typically would cover any issue in terms of conflict that you may have in the connection. Avoid specifying arbitrary CJP, complete joint penetration welded moment connections. So complete CJP, engineers like it. Why? Because they don't have to do calculations. If you specify complete joint over the entire thickness, penetration weld, you don't have, weld is stronger than steel. So you don't have to do any calculations. So avoid doing that. Put the forces you or the fabricator can design for them. And you will use fillet weld, which is a lot more economical than CJP. Favor fillet welds over groove welds. So CJP is one type of groove weld. So groove weld requires typically preparation, a shape, cutting, you know, preparing, you know, specific angle, etc. Avoid that if you can. Okay, favor fillet welds. Okay, choose efficient diagonal brace. So so it depends on the loads that you have for diagonal braces, whether it's for what application also, for stability, for wind forces, for seismic applications, etc. So single angle, this is good for small loads. If you have small loads, you can use a single angle and design. Use L6x6, L5x5 if it's enough, L4x4 it's enough. Double angles, efficient connections in double shear boards. If you use double angles, they will be good. You can use double shear, it will double the capacity of the bolts in shear. HSS, highest braced strength per pound of steel. So typically these are efficient, especially if you use circular or square, because you have the weak axis is equal to the strong axis if you are checking buckling, let's say, of the braces. So they are efficient members, let's say, and they are used a lot, especially for seismic applications and also for other applications for higher loads, probably that are not enough for double angles or single angles. W shapes. W shapes typically will result in a little bit more complex connections, but maybe this is the only choice that we have. And typically those are used when we have high axial loads, such as in high-rise buildings. That's what I have seen. Massive braces in high-rise buildings, HSS will not be enough, so use W shapes. Here, these are examples. So if you have a single or double angle connection, you can see the arrangement on the left. Okay, so bolt through the gusset plate, simple. If you have HSS brace, you basically, we cut the brace, the HSS, and slide it into the gusset plate and weld around it, as you can see. That's also, this is nice because, I mean, it's easy. I mean, even the weld here is easy. But if you use W shape, you can look at the connection. So you will end up with a little bit more complex connection because you have to connect the whip and the flanges, okay? And both flanges, as you can see. Choose slopes of diagonal braces at 35 degrees to 55 degrees. Okay, so the angle is important here. So for the brace to be efficient in resisting the load, the angle is important. So a brace at 20 degrees will not resist really much load. So between 35 degrees to 55 will be efficient. 45 will be the most efficient. Okay, so so instead of using a brace like this across the entire braced frame, maybe you can change the angle by using this configuration. See? So here you increase the angle, okay, by changing the configuration, and the resistance would be more. And also the connections will be better. See that? So if the angle is small, look at the shape of the gusset plate that you will have versus this, okay? Verify that framing can be installed. I mean, we show braced frame like this, members like, I mean, just single lines, okay? So make sure that this can be done in the field, okay, showing, the work points and, the center lines, the interaction of the center lines, having something like this versus, something like that. Okay, I mean, this is geometry of the braces, the direction of the braces. We can do that. So verify that. Make sure that this brace can be installed at that angle. And it will come with the gusset plate and the other members like this. Configure framing to minimize the number of beams. Here we have the same shape. Look at the two configurations. The one on the left, we used girders in the long direction, beams in the short direction. That's opposite to the rule. Okay, typically we have the girders in the short directions, the beams in the long direction. And that's what we have here. The girders in the short direction, the beams in the long direction. So see, we reduce the number of pieces per the rule that we discussed at the beginning, okay? I was told a question here that gusset plates are designed by the fabricator. Well, yeah, I mean, we talked about if you delegate that, they will design it, but you can set the geometry. And I talked about that when I said we can have like a schematic for the gusset plate and the member together, and have symbol A, B, C, D, and then show the dimensions A, B, C, D, you know, of the geometry. So even if it's designed by the fabricator, try to create the geometry or visualize the geometry to see if this is doable or not. Okay, so again, eventually you are the designer of the building, not the fabricator. The fabricator is one of the team members, and he's helping you, you know, as this is connection design is a service that the fabricator give to projects, okay, to, of course, bring job to the fabrication shop. Yeah, it's a service, but eventually you are responsible for that. So you can give the fabricator a schematic of how the gusset plate should be, and let the numbers, let the fabricator run the numbers. You have to give him the forces. Let the fabricator run the numbers. That's fine. But schematically, you have to do that. If you do want to do that, they will do it in their own way, probably, and then you have to review it, and there might be probably they will come up with something that, I don't know, based on their knowledge, this is enough. So typically, you have to decide after that if this is okay or not, and it will end up probably changing the design or accepting the design. Of course, it depends again also on the level of experience of both the engineer and also the engineer who's designing the gusset plate in the, you know, for the fabricator. Okay, maximize slab span to minimize number of beams. See here, again, same slab here. We chose the spacing is to be 6 feet. You have a slab, 5-inch slab for 6 feet spacing. So the 5 inches is okay for the 6 feet. Okay, now if you increase that to 10 feet, probably you need a thicker slab, but you can minimize the number of beams required. So here, this will result in fewer pieces, less steel weight, fewer connections, fewer crane picks, more tributary area per beam, greater live load reduction, more mass per beam, that's less vibration, thicker slab, that's greater composite beam moment, okay? There are significant requirements for connection design for seismic systems with R greater than 3. So if you can design a building with R equal 3 systems, that would be great. This way, you don't have to use any seismic provisions. You need to use only AISC 360. Typical connection design without paying any attention to seismic. Seismic requirements could be a lot. So R equal to 3 is a system as defined that's not required to be detailed for seismic. That's the R equal to 3 system. So if the selection of the structural system according to ASCE 7 depends on the area where you are, if this is enough for your building, do that. If you have to use more than 3, that's fine. We have a procedure for that, which is the seismic connections, and you have to follow that. Ordinary steel braced frames, meaning R equal 3.25, and ordinary steel moment frames with R equal 3.5 are not so ordinary. They are called ordinary, but the requirements to design them are a lot more than what is required for R equal 3. Orient columns and moment frames for strong axis. So you see here, if it's a moment frame, we know this, that we have to orient the columns in the strong axis because of the drift, so strong moment of inertia. So if you have something like this, like the top, you will have 20%, each connection will take 20%. If the orientation here need to be different, maybe there is a moment connection in that direction here, in the middle one, on the other direction. But for that direction, to have a moment connection in the weak axis like this will not be so efficient. So this will take 11%. These ones will take 26% each, and the last one will take 11%. Okay, instead, eliminate the moment connections at the end columns and use these like this, this actually basically 2 moment frames, and this will give you 2 moment frames only, and they will be sufficient, and you have to, each one will take 33%, okay? Strong access, so here, this is an example where you are connecting moment connection to the flange versus the web. See, when you are going into the web, see what happens. See the top here, see the extended plate that comes from the web inside the beam. That's an extended shear plate here, versus this is a standard shear plate. There's more limit states to check here. See, there's more material, there's more weld, there's more cutting, to fit elements in. So that's why we need to avoid moment connections to the weak axis. Okay, run heavy moment connections basically through the column to simplify the detail. Okay, look at that. So here we run the column from the bottom to the top, typical, and then we have beams from both sides, and look at the connections, the heavy girders that are needed to transfer the loads, versus you run the beam straight, you stop the column here, you have stiffeners plates to match the column flanges here, and then have another column at the top, and look at the connections, how simple they are compared to this one. Okay, so things like that will make a difference. Run cantilever roof beams over the column. So instead of having a column in the right, instead of having column with similar, one beam from here, one beam from here, you have a top plate like this that will transfer the beam for the cantilever. Instead, no, have a cap plate at the column here, run the beam on top of it, have stiffeners like that, okay? Minimize the use of little pieces of steel. So brace angles, relieving angles, bent plates, stiffeners, web doubler plates, little beams. Okay, we talked about this. Okay, minimize the use of those. Here they are. Here we have some examples. So for example, here, instead of using, for example, these small beams here, okay, change the orientation of the deck. So the deck is running this way. If we want to keep it running this way, we have to use small beams here. Instead of doing that, just change the orientation and let it span between this beam and the edge beam. And then you minimize, you eliminate all these small pieces. Okay. Avoid skewed beam to column connection. These are very complex, difficult to detail. Change the orientation of the column, make it square. But like this is going to be very complex. Avoid full depth stiffeners where possible. So here we have, for example, a beam coming into a column, column coming into a beam. So we need stiffeners here to strengthen the web. So to transfer the load, we don't need to extend these stiffeners all the way down. Okay, because here, if you extend them down, you have to cut them to fit the fillet, the curve of the web, so there's no need for that. And here, the same thing from the bottom to top. Simplify base plates and anchor rod details. Okay, I mean, use larger base plates, if you can, larger, square, okay, if you can. If you can't, where you have a wall, you have to fit it at the wall, okay, we have no options and we do that, okay? But where possible, use larger base plates to distribute the load, to allow welding around, the column, and also allow installing the boards, okay? Hanger connections. So we have hanger connections, we have to transfer some load through a hanger connection. So we may have different configurations here. So we could have, this basically a pipe here or HSS. This is the beam. So the load is transferred through this. So, through a pipe. Here we have to have stiffeners. So we have a cap plate with stiffeners like this. So that's also avoid pipe hangers. Okay, they will, of course, here we have to have, welding here, there, small limit sets, to check. We would need stiffeners here as well. Now, a better solution would be using an angle connector. So here we use a plate like this, like a gusset plate like this, connected over the entire flange with stiffeners to the top, and the load will be transferred like this. So this is better than that. But the best solution is basically just have a plate along the web, okay, a plate along the web, and then have an angle coming down to transfer the load to the beam. Okay, the connections here are much simpler, and also there is no stiffeners in the beam above, okay? Understand the fabricator's preferences. Shear connections, moment connections, braced frame connections, truss connections, etc. Try to understand. So today, many jobs are design built. So you'd have a fabricator from day one. Try to understand what are their preferences. This will simplify things in the process. Avoid torsion in W-shaped beams. So if you have torsion for whatever reason, you could have a beam supporting brick. Okay, you could have a slab edge that is long, like that. This would need kickers to avoid torsion. Okay, so open sections are weak. Closed shapes are stronger. So instead of that, you can use closed shapes. Camber. Okay. So when we have deflection issues, we camber the beams up. So camber is expensive. It's not something that we get for free with the beams. So do not. So here we have some rules, for camber. Do not camber beams in moment frames and braced frames. If the beam is part of a lateral system, do not camber. Do not camber short beams that are less than like 25 feet. Do not camber light beams, small beams, W8s, light beams. Do not camber them. Typically, if they are less than 19 pounds per linear foot. Do not over camber. So camber for 75% of the slab plus the steel weight. So do not camber for 100% of the weight, or 110, sometimes 110% of the weight. Or camber to 75%, which should be enough to minimize the deflections on your beam. Specify additional concrete to be poured to achieve level floors. So when we don't camber and have deflection, so after they cast the concrete, there will be deflection. So there will be concrete needed to level the floor. So that's why sometimes we need to camber for a certain percentage of the dead load, like 60%, 50%, 75%. So when the dead load is there, it will be almost level. If not, you need to specify maybe a little bit more of the dead load to make it for the design, in case they add concrete to make it level. Include ponded concrete load in the design. That's what it is. So it's all fresh concrete. Do not specify camber less than 3/4 of an inch. If you need to avoid 1/2 inch, don't camber. I mean, you could do something else, increase the size or anything. If you need more than 3/4 of an inch, 1 inch, 1.5 inch, the issue is, then yes, camber. Do not specify that camber be measured after erection. Do not require that. I mean, just require whatever it is. Typically, they are accurate. Compare camber cost to material cost. So ask about how much does it cost to camber a beam versus if you increase it by 1 or 2 sizes, what is the difference in the cost? Is increasing the size cheaper than camber? Then do it. If not, you can camber. Okay? And that's it. That brings us to the end of the session. If you have any question, I'll be glad to answer it, or you can reach out to me by email at this email. Any questions? Okay, well, thank you, sir. You're welcome. Okay, do stiffeners need to be directly over or under the load? So typically, yes, where we have, the load concentration is. So if we have a concentrated load coming from, let's say, the top flange of the beam from the wound connection, then the stiffener in the column need to be at that level to receive it. If the load is coming from above, from a column that's sitting on a beam, okay? So then the stiffeners need to align with the flanges to transfer the load. So typically, yes, to have a direct transfer of the load. When designing, excuse me, when designing a frame to support a structure designed by others, what value should I use when designing a frame to be supported by a structure designed by others? Yeah, well, I mean, that's a good question. And you have to understand what was designed by others. Like if it's old or new. And if it's new, what value they used? So let's say it's a new building that was designed by, say, somebody, it's concrete, and then you are designing steel on top of that, and you're using a different system. So what value do you need to use? So that is according to ASCE 7, the minimum loads standard. The minimum loads for buildings and other structures is standard ASCE 7. So there's like there are provisions for combination of structural systems that will give you what value to use. Okay, if it's an old structure, well, that's a different story. Then we have to understand what that other structure is, when was it designed, and how do we classify it according to today's standard. Okay, and then if we are analyzing both together, then we have to choose the appropriate provisions from ASCE 7. New similar to steel container in high size material. What do you mean by that? New similar, that's a new structure, you mean similar to steel container in high seismic zone. Well, I mean, we need, okay, so we have two new structures. We need to understand what is the structural system for the container that you're talking about for the new structure that you're designing? Are we using R4 and R5 for each one of them? Are we using R6 and R3? So you have to specify what is in the what are you designing for? Is it R equal 3? Okay. The container, what is it? What R value they use for the container design? So if they are different, then you have to follow ASCE7. If it's new, if they are similar, then it's 1R. It's a new structure similar to steel container. I designed the frame for container to sit on and be connected to the frame is connected to steel pipe piles. Well, I mean, you know, again, what is the R value for the structure that you did not design for? Do you know it? Well, yeah, I cannot answer that. So there should be something. I mean, somebody should be able to answer that. So so there's an R value, you know, for that. And then your structure, it has an R value, so you can specify that because you are designing that based on the seismic requirements, because it looks like you are in a high seismic area, or you are designing for seismic. So you need to know. If no one knows, then maybe I would assume R equal 3, but you need to check if R equal 3 is allowed in your area. Even in California could be, but like for small structures and high structures. So if no one knows, probably you need to investigate that structure that somebody else designed, but you said it's new, so somebody should know. Okay, and then maybe it's not detailed for seismic. So if it's not detailed for seismic, I guess probably you have to go with an R equal 3 or less. But this has to be justified with somebody, not me, because I have not seen anything. But that's how I will approach it. So you evaluate it, you look at it. Okay, this is what I have. Check with the local jurisdiction engineers in the city, for example, or in the county, or I don't know where you are, or wherever you are, especially if it's high seismic. And then, okay, this is what I have. No one gave me an R value, but I think the designers should. If not, the local jurisdiction. So what do I need to do with this? Okay, I did not design that. What R value do I use? They will give you that. So if you have two R values, then go to ASCE7 and see how you combine both together. Okay, or how you design for both together. Okay, any other questions? You're welcome to email me. That's fine. Okay, thank you, everybody. Any questions, please email me. Thank you. Thank you, everybody.